My name is Nelson Dichter. I'm going to talk to you today about the evaluation of thermal energy storage for utility grid operators. I'll get more into what that exactly means in a little bit, but I'll start with a background on myself. I've been working with Mark Madera and Teresa Pisticchini at the Western Cooling Efficiency Center. I started as an undergraduate student in 2008. In 2010, I became a graduate student, and I completed my master's degree in 2012 when I was immediately hired as an assistant engineer. I'm now an associate engineer, but some 10 years later there. I did my master's thesis on computational fluid dynamics and looking at particle deposition of sealants in transverse flow, essentially. But my main focus while working at WCEC has been largely on doing building energy simulations. And so I'll kind of be working into that a little bit with what we did here. So let's go on. So thermal energy storage is actually a fairly broad term. It can be basically you're storing energy in the form of heat in some way. It can be either as cold energy or as hot energy. I'll be talking today about storing it as cold energy, but you can also store it as hot energy. One of the most common ways of doing that is in things like molten sodium, where you'll basically melt salts and store it and then use that later the heat later to create steam and turn a turbine or something like that. What I'll be talking about today is thermal energy storage in the form of cold energy, meaning that you use mechanical work to create a cold reservoir of some kind and you store it so that you can use that cold energy later. This is a typical diagram of a thermal energy storage system. It could be either an ice storage system, where the storage is in the form of a big block of ice, or it could be stratified chilled water, where you have a large tank that's insulated and you just have cold water in there that you draw the colder water from and you replenish it with a chiller. Typically this is a glycol loop, so you've got a chiller operating on a glycol loop, and they can operate in three distinct modes essentially. You can either just be running the chiller, so the storage would be disconnected by the valves, and you would just be running the cold glycol through a heat exchanger which can cool a building. Another way you would run it is when you're charging the thermal storage, so the valve for the heat exchanger will be turned off, you're no longer providing cooling to the building, but you're pumping that glycol through your storage tank and either creating chilled water or you're creating ice. And the other one is to discharge the thermal storage, where the chiller is actually off and the glycol is just running through the storage, so you're either melting the block of ice or you're using the stratified chilled water tank to then run the cold glycol through the heat exchanger. So thermal energy storage, what does it actually do? Right? So you can use it to shift the thermal load from peak hours of the day. So you can run the chiller at night and then not have to run it during the day at all and use your stored thermal energy to provide all the cooling for the building the following day. So you don't have that peak in electricity demand when the weather gets hot outside and when people are in the building doing lots of activity. So basically the impact to the utility grid, which is what policymakers care about, is it's the energy that would have been used when you use a thermal, that would have been used to run the cooling system, but instead you're using the thermal energy. So this is important because you can think of thermal energy kind of like a battery. You're essentially storing energy, but it doesn't work in the same way the battery does, where a battery takes electricity from a power generation source or the grid and then later puts it back onto the grid. It'd be very inefficient to use thermal energy that way. Even if you were storing it as heat energy, you're still looking, your round trip efficiency, grid to storage to grid, is really low with thermal energy, whereas with a battery it's fairly high. What you can do is you can store the thermal energy and then later use it as thermal energy, so you don't have that conversion process of going back from electricity to thermal back to electricity. You're just going to electricity to thermal and then just using the thermal later. And so it creates a lot of challenges from the utility perspective, because if you're trying to provide value, you're trying to evaluate essentially what your customers are doing. You want to reward them for shifting their load off of the peak onto the nighttime when there's a low demand for electricity and electricity is cheap. It's easy to do it with a battery because you just measure, the voltage and the current coming out of the battery. How much did you put in? When did you put it in? How much did you take out? When did you take it out? It's a one apples to apples comparison. But with thermal energy, you're essentially preventing the thermal load that's coming from the building from ever actually getting on the grid. So you're trying to measure something that doesn't actually happen. So that makes it very difficult in that sense. Another one that's tricky is that as the ambient temperature increases, other forms of energy, like your batteries or say a generator, things like that, their efficiency goes down. So does a vapor compression system that you would normally be displacing with a thermal energy system. That means that as the ambient temperature goes up, the value of thermal energy actually goes up as well, because the efficiency of the load you're disconnecting from the grid is going down. Feel free to stop me with questions at any time. I'd prefer for this to be kind of a two-way conversation rather than just me speaking at you. All right, so why is this all important? The cooling demand in the globe is rising significantly every year. So in the USA, as of 1955, there were 2% of homes with AC. It went up to 50% in 1980, and in 2016, 70% of all buildings in the US have an air conditioner on them, pretty much. And that's kind of considered to be saturation, somewhere between 70 and 75%, because there are buildings that just don't need air conditioners depending on where they are. China has followed a similar arc. They were a little bit behind us, but they've pretty much, at least in urban areas of China, they've caught up with us, where pretty much 100% of the buildings in urban China have air conditioners at this point. And one fact that I thought was really amazing when I came across it was that if the cooling strategies used in the US were deployed in India, there's so much cooling demand there that the metropolitan area of Mumbai would account for 24% of the entire electric cooling demand of the United States, just from that one city. So it's a big problem where the rest of the world is, we got economic development, global climate change is playing a big part because it's actually reducing the amount of cooling or heating demand that you need, but it's increasing the global cooling demand. Population growth obviously is playing into it as well. And also compared to other electric loads, an increase in cooling demand puts a disproportionate amount of impact on peak demand. So we're having this huge spike in peak demand caused by cooling equipment. So anything that we can do to basically shift that load or to flatten it is extremely advantageous, and thermal energy storage is one way of doing that. All right, so another thing that kind of compounds the issue a little bit is the penetration of renewable energy. Renewable energy is great, but one of the problems is, aside from hydroelectric, it's fairly intermittent. We can't really control. We can predict when the sun's going to shine to a degree, but we can't turn it on and off. And same thing with the wind. So we have this ability to generate electricity, but not necessarily have it coincide with when we need to use it. So being able to absorb extra load when there is extra energy available and then shift it to times that we need it with things like thermal energy storage is very important. Some interesting facts is, so in the USA, we went from 122 watts per capita to 207 watts per capita from 2000 to 2013, so that's a pretty steep increase. The rest of the world is catching up with us. The countries with the most renewable energy actually tend to be mostly geothermal and hydroelectric. Countries in like the northwestern Europe area, you got Greenland and Norway, both have enormous, it's several kilowatts per person of renewable energy that they have connected. So, how do utilities deal with thermal energy storage? Well, the utilities they kind of do what's called resource adequacy planning. So, their goal, their mandate essentially is to one second, sorry. The goal is to maintain adequate reserve margins such that involuntary load shedding due to inadequate electricity supply only occurs once in 10 years. And that generally happens when you have a huge heat storm. Everyone turns on the air conditioner, they can't keep up with it, and it goes down. So their goal basically is look, okay, what is the hottest that is going to get like once in 10 years? It's called a 1 in 10 year heat storm. And they try to have enough reserve margins so that they can meet the load, or almost meet the load at that 1 in 10 year heat storm. So they only ever have to do basically either a brownout or a rolling blackout once every 10 years. So the way that they do this, the way that they try to achieve this is with two methods primarily. There's demand response, which is where they will announce times during the day when they say, okay, you guys, if you can reduce your load during this hour, we'll actually pay you for it. And there's permanent load shift, which is where they'll incentivize a program that will permanently reduce the connected load of a building. I'll talk more about that later. So, how is thermal energy storage evaluated right now? So thermal energy storage offsets the thermal load before it's transferred into the electric load. Like I said before, this is basically you're trying to measure something that doesn't happen. you basically say, okay, I turned off my chiller, I ran my thermal energy storage, I didn't draw power from the grid, but how much power would you actually have drawn if you were to have used your chiller is kind of, without sophisticated modeling, it's very difficult to really determine that. So as I said, general practices are demand response, and the way that's usually evaluated is called a 10-day average baseline. So what they do is they look at the past 10 days, usually it's restricted to weekdays, and they exclude holidays, and they say, okay, for this hour, how much energy did you use in the last 10 days during that hour? Okay, the average of that for those last 10 days is your baseline. So if you can use less energy than that, then we'll pay you for it. If you use more than it, then you're over your baseline. Sometimes you'll get dinged depending on what type of program you're enrolled in. But so there's a couple issues with that method. One of the big ones is that when a heat storm happens, that means the last 10 days weren't necessarily that hot. But then all of a sudden you're asked to reduce your load during this heat storm, and the amount of thermal load you have to meet is much greater than it was in the last 10 days. So your actual baseline is significantly higher than what it would be. Another way they do it is with, as I said, permanent load shift programs. So, and the way they do that is they basically use a computer model to model a building, and they'll say, okay, annually, what is the peak demand of that building? What's the most amount of electricity it's ever going to draw at one time? And then you propose a project that you're going to do on the building to reduce that. And then basically they still model it and say, okay, how much did you reduce it by? And then after you do that, they'll give you, say, okay, we're going to write you a check for this amount of money tentatively. Do your upgrade, and then after the upgrade, they'll come back and measure it and see if you actually achieved the peak reduction that they set out. However, when they do that measurement, they're not really measuring the peak because you can't really create a 1 in 10 heat storm event. What they really are doing is they just measure whenever they go out. They kind of pick a hot day, but they go out and measure what your building is consuming. They take the ambient temperature into account, and they look at their model and say, did this match up with my model? If you're lower than what the model was, they'll adjust the peak value. If you're higher, they'll adjust the peak value accordingly. The problem there is that it tends to have a lot to do with what weather file you use in order to create those models. And I'll get into that a little more later. All right, so what did I actually do? I was looking into this evaluation method, and I basically said, okay, how accurate are they? We used whole building simulations on 3 different building types. They're all commercial. There's a 10-story office building, a big box store like a Target, and then a hospital. And the cooling systems that we looked at were direct expansion RTU, and then 4 different chillers. We did variable speed ones and water-cooled ones as well. So one that was, they're all up there. There's the air-cooled constant speed, air-cooled variable speed, water-cooled constant speed, and water-cooled variable speed. We used Trace 700 to generate the load profiles of the building. And the rated cooling capacity of each unit essentially was set to be the maximum load for the building. So at 100% PLR, the rated capacity at least would be able to meet the load for the building. Yeah?
I was just wondering, how common are thermal?
There's on the East Coast, there's quite a bit. It seems like they've been sold largely to schools. Some hospitals have installed them. One of the big things about them is resiliency. So you can have, depending on what size system you buy, you could have several days worth of cooling stored in basically an underground tank. They are a lot cheaper than, say, batteries are, and they're also like a lot more environmentally friendly. They're pretty much recyclable materials. It's basically a tank that has, I can't remember what they use for insulation, but it's a pretty eco-friendly insulation. It's the most of them. I can't speak for all manufacturers, but the ones I've looked at are. So they have, the one disadvantage they have to, say, batteries is their energy density. Obviously, the energy density of ice isn't similar to lithium polymer batteries. Big advantages are the ones I listed. But, yeah, Teresa?
Your direct expansion RTU.
Kind of, and there's also, so I was going to go into it, and actually I was about to go into it before the questions. So that I can just do it now. There's what's called an organ transplant, which is a program that a lot of utilities have adopted where essentially you go to, like I say, what's called a boxcar, which is a really big RTU, and you gut it. You're not allowed to take away the box, but you can take every component out of it and put a chiller into it, say. And you basically get to base your calculations for how much energy you save based on the nameplate that is on that box, which is why they call it an organ transplant. So that's why we looked at direct expansion RTUs, because you can actually pretend like you're displacing the load from a direct expansion RTU, even though you really have upgraded equipment now, and you're displacing a much lower load. Does that make sense? Have I explained that well?
So is that a trick you
It's not. It's a program that they have established essentially, and it's not an official program. It's something you have to kind of apply for, and it depends on who your account representative is to whether or not they'll let you do it. I guess. I mean, I don't know all the politics behind it. I just know this is a practice that is commonly done and it has a name. And it's called organ transplant. And it's basically in order to get them, because they get two things. They get to disconnect a really inefficient system from the grid, and they also get to have then thermal energy storage to reduce the peak. So they're paying for it, basically a large efficiency upgrade, and they want the nameplate left there so that in their accounting they're like, oh, why are we crediting them so much like the demand response energy when they're only disconnecting like a really high efficiency chiller? It's kind of weird, but that's how the system works right now. I'll try to go through this one a little quickly. It's kind of some boring technical stuff, but so sizing the systems was actually fairly complicated because I had to come up with a system of sizing that was, I couldn't just go in there manually and size everything. I had to have it be something that was consistent across the board, even though we had 3 different building types and then 3 climate zones. So there was 9 different cases essentially that we were looking at with 4 different units. All had to be sized somewhat differently depending on what they, or 5 different units that had to be sized differently depending on what they are. So I basically first started with the rated cooling capacity of the units. I set them to be equal to the maximum annual cooling load, which doesn't necessarily mean it'll always meet the load. It means that, so I mean rated conditions, I don't know how much everyone knows, but they're the performance of the unit at specific conditions, which I believe is 95 degrees Fahrenheit, 98 for the HR test points.
That's
95,
95.
yeah. So in a lot of the weather files we looked at, regularly got up to 110. So it meant that they were actually undersized. Because the capacity goes down as the outside air temperature goes up. So they were a little bit undersized for the building, but they were close enough to satisfy the cooling load for the building most of the time. The cooling towers kind of proposed a unique problem because the interaction between a cooling tower and a chiller is actually fairly complicated when you try to model it. I basically looked at what the goal was for HVAC contractors and engineers was to maintain 85-degree water. That's what you want to see going into your chiller to cool it. And so I set the coolers to be able to deliver 85-degree when the chiller was running 100% PLR at rated conditions. So a similar thing still that was slightly undersized for, say, 110-degree day, but it was pretty close to what you would actually want to see. Figuring out how to scale, let me see. Yeah, I mean, I think that you guys can see it all there. I don't know if this stuff is really terribly important. I'm going to go forward in the interest of time. So there were 2 things I modeled. It was demand response and the permanent load shift program. So when I was modeling demand response, I picked the 12 hottest 4-hour segments of a day out of the year and basically said, okay, those are going to be my event days that I'm simulating for this period. And then I used the 10-day average baseline that I described before and applied that to those days to figure out what their baseline would be for that time. And I used the energy simulations to look at what the actual energy use of the chiller would be if you had run it during those 12 event days. And so essentially I looked at the energy use of all the pieces of equipment that would be disconnected. So in a chiller, that would mean, if you're talking about an air-cooled chiller, you've got the condenser fan and really it's just the condenser fan and the air-cooled chiller that you end up, the condenser fan and obviously the compressor that you end up turning off. So I left the indoor fan and the pumps still running because you still need those to run the thermal energy storage system. And I did a similar thing for the water-cooled systems where I said, okay, how much energy are the things that would be disconnected going to use during the day? And that would be the pump for the water tower, the fan for the water tower, and the compressor once again. So here's some of the results. We've got the ambient temperature in yellow. So these are the 12 hottest days out of the year. Several of them are consecutive. You can see the July 10th through the 13th were some of the hottest days in the weather file that I was looking at here. This is for the 10-story office building in Sacramento. So I just picked one of them to show here. In orange, you can see basically for when the event was called, this is the predicted baseline. And in blue, you can see the actual amount of energy that the disconnected components would have used if they had been on. So some days it gets fairly close. So these days meant that the days leading up to it, the 10 days before, were fairly, the temperature and the weather was fairly consistent. so that the baseline predicted that the amount of energy is going to be used. But on other days, like this July 10th, so Mondays tended to be the worst because, especially when you're talking about like an office building, no one's there during the weekend, the thermostats are set back. Monday comes around, and in the morning, everything has to kick on, take over a huge thermal load that's in the building, essentially. So you get this huge spike. So basically, in order to save money or to get the demand response credit from the utility, they would have had to offset this entire load and go below the orange load. Basically, they'd only get paid for what was below the orange line. So, I mean, it was somewhere around a 4 times difference there.
So, sorry, the blue line is without thermal energy storage.
Right.
How much an air-cooled?
In this case, is it air-cooled? Yeah, this is a direct expansion RTUs, so this one would be the... Oh yeah, sorry, no, this is air-cooled. Listen to this one, I mislabeled it.
Okay,
Here.
but anyway, that's without thermal energy.
That's without thermal energy storage. So if you were to use thermal energy storage, this line would just be 0. Right? The 0 is the amount of energy you use with thermal energy. Because this is
already subtracted the pumps and fans.
yes, this is only taking account for what I said before. Like, so if this is air cooled, then it's air cooled variable speed is just looking at the condenser fan and the compressor.
Okay, what that would
be. Yeah, what they would use. Any other questions on that one? So here's some statistics on the air. Basically, the average air was generally around 50%. So you'd actually use 50% more than what the 10-day average baseline predicted you were going to use. And then went as high as 76%. So it was a significant error. I mean, the only one that ever got close was the water-cooled constant speed chiller, and that's largely because, and that was only the minimum, so there were times when that one almost predicted it correctly, and that was largely because a water-cooled constant speed chiller is more dependent on wet bulb temperature than really anything else. Which?
That's the difference between the predicted 10-day baseline and your actual baseline.
Right. So it's always positive. It's always under predicting, and usually under predicting by about 50%.
So basically, utilities are
Not for systems like this, yeah. And then here's the statistics for the average for all the simulations I ran, basically. As you can see that they're all pretty much, the lowest one is, 27%, I believe. And then they're mostly all of them have around 50%. All right, so then for permanent load shift modeling. So as I kind of hinted at before, the biggest impact on what type of rebate you get for the permanent load shift modeling, it comes from the weather file. So other technologies, like let's say generators and peaker plants and hydroelectric, they all get rated using what's called ASHRAE 10-year weather point, which is, ASHRAE has a bunch of data for every city in the US pretty much that says, okay, in 10 years, this is the highest temperature you should expect to see in that city. And they have, other metrics for different number of years, but the 10-year one tends to be the one that gets used. And so all those other technologies get rated using the ASHRAE 10-year maximum. And then they take thermal energy storage aside and say, okay, we're going to rate you generally using TMY3. So for some reason, there's this big divide between how they're rating these two systems. Oh, batteries also. Batteries get rated using the ASHRAE 10-year maximum. And that one matters because if you have a large battery inside a storage container, you have to also cool it. And then when the battery's under load, they produce heat. And so the efficiency of that whole system goes down a little bit as it gets hotter outside. So they say, okay, we're going to give you credit for a connected battery based on what the battery would actually be doing at the 10-year maximum according to ASHRAE. So I ended up looking at 4 different weather sources, and I basically want to see, okay, with these different weather files, they're supposed to be standard weather files, how much variance is there between them? So I looked at the TMY3, which was a standard for a long time. Then California, they came up with the California Climate Zone Revision 2 was one that was used up until about 2012, I think. And then the California Climate Zone 2010, which they call CZ 2010, is what has been used since 2012. And then also the ASHRAE 10-year maximum. And I compared those to each other. So here's the results. You can see that the ASHRAE 10-year maximum is significantly higher than the other ones, especially TMY3. And especially, for some reason, especially in Burbank. And those are generally the differences. But when you run them through the simulation, these are the results that you get. I included the rated conditions here. So this is basically if you just go by the nameplate of a piece of equipment and the manufacturer specs, this is how much energy they'd say would be your maximum at rated conditions. And then if you apply the TMY3 annual maximum or the ASHRAE 1 in 10 maximum, what's the difference? And so as you can see, for especially like the air-cooled constant speed chiller, which is the most sensitive to outdoor air temperature, it's much higher if you're using the ASHRAE 1 in 10 as opposed to TMY3. TMY3 and rated conditions tend to be pretty close to each other. I'm getting pretty close. Okay, basically what I showed was everything is inaccurately predicting how thermal energy storage is performing on the grid. So rather than just pointing out the problems, I also tried to come up with a solution. And it is a technical challenge, because like I said, you're trying to measure something that doesn't happen, essentially. And that's pretty much exactly what you have to do. So you have to continuously monitor the performance of your cooling system. And especially with chillers, this is actually fairly easy, because you can measure the water flow rate and the temperature going to and from the chiller, and you can know exactly how much cooling you're providing. It's much more difficult when you're trying to do air side measurements or refrigerant side measurements, but in a glycol loop, it's pretty straightforward. And the idea is with your air-cooled chillers to basically force throughout the year several test points. Say maybe at 6 o'clock at night when everyone's gone home, you can say, okay, it's hot outside, it's a good time to collect a test point. I'm going to run my equipment up to 100% capacity, because you use 100% because you can assume that anytime you're doing any type of demand response or permanent load shift, you're basically going to be running your equipment at 100%. That's what you're offsetting, assuming your equipment is sized somewhat appropriately to your building. And so you can create a performance map by changing the outdoor air fraction of your system, so that you can modulate the temperature that the water coil and the water coil sees, so that you can get different test points. And you basically create a performance map that says, okay, at this outdoor air temperature, this is the amount of power that my system uses, and this is how much cooling it provides. And when you do that, then you can say, okay, when I disconnect my load, I know what the outdoor air temperature is. I know how much cooling I'm providing, because I can measure the cooling coming out of the thermal energy storage system, so I can then use that model to predict this is how much electricity would have been used. And it's a similar system for the water-cooled chillers. You essentially can control the water coming from the water tower. You control that temperature to simulate a peak event in order to create a map of how the system would perform at high outdoor air temperatures. And in summary, thermal energy storage systems, their capacity to offset load is largely affected by the ambient conditions. And the current 10-day average baseline system and the permanent load shift methods for evaluating the systems basically prevent them from being financially incentivized because they're not properly predicting their value. And like I said, the error is as much as 28% for the permanent load shift program when the TMY3 data is used instead of the ASHRAE 1 in 10. Questions? Because there's a lot of reasons why, but the temperature generally has been increasing in California. So as new revisions of weather files have been coming out, then the annual maximum has been going up consistently. As I showed, there was the RV2, which was what was used before 2012, and that had, I can go back to it. I can go back to it on mine and tell you the numbers. Where'd it go? So between RV2 and 2010, it was in Burbank a 4-degree difference in the maximum temperature that we saw. In Riverside, it's a 6-degree difference, and in Sacramento, a 4-degree difference in maximum annual temperature. Yeah, and this is all Fahrenheit. Sorry, I should tell you the units, obviously, but yeah, it's a big difference. So we're seeing maximum temperatures that are happening much more frequently than they did in the past. So I'm not saying TMY3 wasn't always a bad set of data, but as it's moving forward, it's becoming less relevant. And that's why, that's why they had to update the weather files as frequently as they have. I can't remember when the version before 2010 was published, but it wasn't, sometime in the early 2000s, I believe. Yep. Anything else?